Welcome to the first video of our course. I'm taking a look right now at our course outline, which is kind of a snapshot of an Excel spreadsheet. This overview of our first unit, so our first unit is about vectors, uh, motions and forces in two dimensions. This first section will really be review, so I would say this first couple lessons will be things that you have done in Physics 30S. Definitely, if you took it with me, some of the exact same worksheets and things like that. If you took physics somewhere else or with somebody else, all the materials should be familiar, if not like something that you did exactly. We'll be covering these things, so you can take a look at. I won't be covering, one lesson per line here, but you can see the general flow of it, and each of these are lessons from the uh, physicsclassroom.com tutorial. So at any point in time, if things weren't making too much sense, if you can see lesson 1, vectors, fundamentals and operations, vectors and direction, if you happen to stop in at physicsclassroom.com, and here if I scroll up, and if we go look at the tutorial, and if I take a look at vectors here, and here you can see a very, very similar to my outline here. So you got vectors and direction. So if you get tired of hearing my voice, and I can totally understand that, you can also go through and read this, and you'll notice that some of the pictures and things like that I actually use. So this is really a different way of covering some of that material. So the method that I have here is I make a skeletal notes for you, and then we'll kind of fill them in together. So at this point you should have this sheet of paper in front of you, and we'll take a look at this. So vectors and directions. Well, first of all, we have to remind ourselves, what's the difference between a vector and a scalar? So scalars, for example, are going to have what we call magnitude and direction. Oh, I'm sorry, scalars only have magnitude versus vectors, I'm going to go for green on vectors here, have magnitude and direction plus direction. Now, what is magnitude? Magnitude, you could kind of break it down into two pieces. Magnitude is basically a number paired together with a unit. Okay, so right below this we have a space for an example of something that's a scalar. And if you look at this picture over here, if you had a bag of gold, and if I said, how much gold do I have? So perhaps I've got 10 kilograms of gold. Okay, I'll even put of gold in here because it's nice to talk about gold. So I have 10 kilograms of gold. That here would be my number, right? So this would be my number, my 10. This would be my unit. And I don't have any direction here. I can't say 10 kilograms north or 10 kilograms south. So that's just the way it is. How about as a vector? What might be an example of a vector? I could say the wind is blowing at 10 kilometers per hour, right, from the west. And we'll be talking about wind a lot more a little bit later on. So here, if we take a look at it, here's the magnitude part. Here's the number and the unit part, when that constitutes the magnitude, the amount of wind, and then this is the direction, from the west. Okay, so let's see about how to represent vectors. So the first way that we can is in a scale diagram. A scale diagram must contain, first of all, the word scale. Okay, and typically I like this kind of method where you have scale full colon 1 centimeter equals and then something. Okay, now that something afterwards is going to depend upon what kind of units of your vector. Like if it's kilometers per hour, it could be 1 centimeter equals 1 kilometer per hour, so the units change. And also you would change this number here according to how large or how small the diagram is going to end up being. The second thing it has to be is you have to have some type of indication of direction. So I'll say direction indicator. Now it's not quite, did I spell that very well? How about if I'll choose a pen that's a bit nicer here. It's a little bit too kindergartenish, isn't it? How about indicator? There we go. So in this scale diagram, really this is their indicator, and I would even be happier if someone put north there, or somewhere even they put north like this just to say which way. So this is a traditional north-south east-west direction indicator, so that we can actually tell when the line is going this direction, we can tell what direction it's going. What else should it have? Well, it should have an actual arrow in here, and the arrow should be labeled. Okay, so you see their arrow here, and over here there's also a little diagram about how an arrow looks, and we have a naming convention. We usually call this end the head of it, or this side the tail of it. You'll also hear me use the words tip, tip to tail, head to tail, things like that. So it definitely has one end that looks like this, and the other end that looks like it's an arrow. And we should also be able to label. Okay, labeled. So in this case, here's the label, the 20 meters. Okay, and so we should know the magnitude. We should know both things, right? We should know the magnitude, and we should know the direction, because those are the two important parts of the vector. So did we do the magnitude? Here, we'll just check it off. Where's the magnitude? Here is the magnitude, 20 meters. Did we do the direction? Yeah, there it is, the 30 degrees. Okay, now the other thing about vectors, when we write about vectors, we really should have an arrow. This is this part here. Should have an arrow, but Mr. Speiser rarely does. So for example, if we are talking about displacement, if you recall, this is usually the way we write displacement, the change in position. Technically, if that is a vector, we should be writing a little arrow over top, right? Sometimes we do this kind of a shorthand arrow, which is going to do that way instead of drawing them both, because if you do this, you can just do it in one kind of swoop. But I often skip, I'm erasing, I often skip the arrow over top. So if I'm formally introducing a new type of a vector, I might say, oh, okay, here is my velocity vector, like that. But then later on, I'll just put a V in for vector. So I'm a little bit sloppy, and I will not ever take marks off or expect you to remember the arrows unless if I say put arrows over top of the vectors or something. Okay. The next is the direction. I'm going to introduce to you three different ways of talking about direction. So here is a north, south, east, west grid, and how about we use green for the first one? And if we did 30 degrees north of west, okay, 30 degrees north of west, basically point yourself west first. So here you are in the center. Look out west. Now rotate 30 degrees away from that. I think I'm going to try to find an arrow. See, where's an arrow? There's an arrow. Okay, kind of a weird looking arrow. So there we go. So perhaps that would be our 30 degrees north of west, and then we should label in here 30 degrees. Pardon me. So that would be an example of 30 degrees north of west. Now the second one we'll do in blue would be the 150 degrees CCW. So what does CCW mean? CCW means, here, right over here, CCW. It means counterclockwise from east. So you'll see that this actually means it's actually the same direction. Starting looking from east, and now we're going to go 150 degrees this way, counterclockwise. It's actually the same arrow, isn't it? These are two different ways of talking about the exact same thing. Okay. Now the textbook that we use a bit, not too much, but I'll show it to you every once in a while. It would look at the same arrow, and it would say west 30 degrees north. Okay, so I'm not sure how often we'll be using this textbook, but again, same arrow, and it would be more like start by looking west. Start by looking west. Now rotate 30 degrees to the north of it. Okay, so it's actually quite similar to this one, except that the N and the W get switched directions and there's no of in between. Alright, so the next section here is components. It says a vector can be broken down into components, and we use subscripts. So one example that you'll be familiar with is if I say here is, we did this a fair bit in grade 11, if this is, say, my applied force, I could say, well, how much is the x component and the y component? So maybe I'll use red. I could say, well, this is the amount that it goes in the x direction. So I would write FA and then with a subscript x, and this is the amount that it goes in the y direction. So this would be FAY. Okay, and it might actually be easier if I draw my original FA over here so there's just a bit more room for everything to be seen. There we go. So what we say, if this is the original vector, these two are components. Okay, so in a diagram, I can take out the original one and replace it with the two components, FAX and FAY. Subscripts are, if you recall, like from using Microsoft Word and stuff, that's where the X gets a little bit smaller and a little bit lower than the rest of them. So later on in this course, we're going to be doing some things in relative velocities. So we have, these are velocity, VOG. So I'll be going over this later, but this particular one, I don't actually say VOG, I say VOG. So that is the velocity of the object with respect to the ground, VOG. And this one would be the velocity of the object with respect to the medium, and this is the velocity of the medium with respect to the ground. So clearly, I'm not asking you to memorize them or anything. I'm just having you note that v is the name of the velocity, and then the subscript just sort of tells me about which component it happens to be. The other thing about vectors is that we can be talking about, if we only want to talk about the magnitude of a vector, then we put absolute symbols around it. So let's say if I said I had a velocity v was 10 meters per second east, right? If that's the definition of this vector, then the absolute value of v would just be 10 meters per second. Okay, if I just wanted to talk about its magnitude, I would do the absolute value. So if you recall how that works, the absolute value of, say, -3 is equal to 3. So whatever is inside of those two vertical lines, we just make the positive. This is when we're doing straight numbers and scalars and things. This is how we do this with vectors. Okay, on to the next page. Here's some examples from the worksheet that I'm going to be asking you to do. So it says, what is the counterclockwise direction and what's the magnitude? Now, unfortunately, I do not have a protractor with me right now, but what you do is you get your protractor out and you would measure, starting counterclockwise. So this CCW, it's a bit confusing. It's not counterclockwise from west, it's counterclockwise from east. Okay, so you always measure off the east axis, or in pre-calculus we say off of the positive x-axis. So we do it the same way in both disciplines. So I would measure this. So far I've gone 90 degrees, now I've gone 180 degrees, and now I've gone some extra number of degrees. Just estimating. Let's say that this last part is about 60 or so. So that, how many would that be? That would be 180 plus 60. So if my math's okay, it'd be something like 240 degrees. Okay, and I don't have to write CCW, but I can if I want, just to be specific. Okay, so that'd be, the direction is 240 degrees, and then the magnitude, I would get my ruler out and measure that, and I'm not sure, maybe it's like 2.1 centimeters or something like that. So we'll see. So that would be one example from the worksheet of how to do those ones. This part here, it says, consider the grid below with several marked location. Determine the direction of the resultant displacement for a person who walks from location. So let's do the first one, from A to C. Okay, so if I was to start here and I was to end over there, determine the direction of the resultant displacement. So the direction from here to here. Okay, so I have to figure this out in there, I'm doing a really bad job, and counterclockwise from east. Okay, so I would say, all right, I would start from here and I would measure what that angle would be. Why don't I erase this and see if I can do a better job of this here? Okay, so between A and C, I need to draw a line. And there, I didn't do a great job of it, but there's my work. And now I would say, okay, I'll do it in red. Looking at the number of degrees, here would be 90, here would be 180, here would be 270. So I could get my protractor out and measure that last part and then add it to 270. So just a guess, I would say maybe about 270 degrees. Something like that. Let's take a look at the last one there. It says, determine the direction of the resultant displacement for a person who walks from I to K to B. Okay, so they're starting at I. Here's I. Then they're going to K, and then they're going to B. Okay, well, to tell you the truth, the K part doesn't really matter, because when we're talking about a displacement, we're talking about from where they started, you draw the arrow, and where they ended, that's where the arrow ends. I'm going to draw one of my really huge arrows here. So it's going to start here, and it'll end over there. Oh, and I can't quite do it perfect. There we go. So there is my arrow. It's a huge one. And when we do this counterclockwise, again, we would say, okay, start here, 90, 180. I would have to measure that last part. Maybe that last part's 20 degrees, so that would be 200 degrees. Again, you're going to have to use a protractor. Sorry, a protractor to figure out that angle. I'm just guessing the 200, so I may not be exactly right. Question number 9 says, a short verbal description of a vector quantity is given in each of the descriptions below. Read the description, select a scale, draw a set of axes, and construct a scaled vector diagram to represent. Okay, I will do A, and you guys can do B. Actually, I'll do A, and I think there's more in the thing. Kent hold it no more, excused himself from class, grabbed the cardboard pass off the lecture table, and displaced himself 10 meters at 170 degrees. So clearly this is a school where they require a cardboard pass just to go to the washroom. Aren't you glad you go to our school? Okay, I'm going to kind of make a grid here. I think I've got an auto. Oh, there we go. I got this gritty thing here that I can use. There we go. So that kind of makes my XY grid, and I'm going to label this here. I'm going to say this direction's north. This one's east. This one's south. This one's west. So I need to go 170 degrees. And again, my arrow is going to be really thick and yucky, but 170 degrees means it's going to be about over there. Okay, assuming that this little piece there is about 10 degrees, so this is 170 degrees. So I can label this like that and say 170 degrees. And I should label this as 10. Oh, but I should have thought about my scale. Now on that piece of paper, when I draw out scale, so I'll write the word scale, 1 centimeter equals, now you have to think about this, meters, what number to put here. Like if I put a 1, then you realize that this line has to be 10 centimeters long, right? I don't think I have 10 centimeters of room there, so I'm going to have to choose a larger number so that my line is shorter. So what if I say 1 centimeter equals 5 meters? Okay, so then this line in real life should be 2 centimeters long, right? So you get your ruler out and you make sure it's about 2 centimeters. I don't label it as 2 centimeters, however, I label it as 10 meters because that's what it is. That's what it represents. Okay, so just to be clear, you don't, when you label this, you don't label this 2 centimeters, you label it whatever this vector was. Okay, oh heck, I'll do number 2 for you as well. Let's try it out. So I got a nice big, get another nice one of those things there. Okay, it says Mark is tardy, took an extended lunch break and found himself hurrying through the hallways to physics class. After checking in at the attendance office, oh, again, a harsh school, Marcus moved with an average velocity of 5 meters per second at 305 degrees. Okay, so I'm going to just, indicate that's north, and this is south, this is east, this is west. I'll start off with the scale. I really should have started with the scale last time too, so I'll say scale. 1 centimeter equals, so I think I have enough room to physically have 5 centimeters. So if I say 1 meter per second, then my scale diagram needs to be 5 centimeters long. Okay, I hope that makes sense. Now I'll draw my arrow, and it needs to be at 305 degrees. Okay, so just thinking, this is 90, this is 180, this would be 270, so I need to have my angle another 35 degrees. So another 35 degrees over. So when I get my protractor out, which I don't really have, I make sure it's just right. So I'll go like this, and I'm pretending here that I drew this 5 centimeters long, And I'm also thinking that this entire angle here is 305 degrees. Okay, so there we are with the scale diagrams. Your homework, and I look forward to seeing this completed, is to do this worksheet here, the Vector 1 PDF, and then also to do the MOP sublevel 1. And so that is within Vectors and Projectiles sublevel 1. All right, thank you very much. I will see you in class.